Thank you, Megan. In addition to the material I'm presenting today being very cool, I'm sitting at a beach in California. We're currently on vacation and it's 9 o'clock in the morning. So you'll hear a spring in my voice for various reasons.
So jealous.
Well, I'm awake at 9 o'clock in the morning. That should tell you how committed I am to this workshop. So thank you, everybody. I know it's the last talk. I'll try to keep it quick and fun. We've been working extensively with various kinds of exoskeletons for over half a decade now. And classically, we started with the passives out there. We started with several of these exoskeletons even before they were in market. For instance, with the ExoBionics device, we were working on pre-market versions, doing some biomechanical evaluations and going through device iterations in terms of assessments of the human being's physical experience in the exo. We have worked through lab-based studies and field-based evaluations of several of these devices as well. I think I'm preaching to the choir. I probably don't need to do much about what are the classical opportunities and risks and, the challenges with looking into exoskeletons, especially when you're looking into occupational implementation. So I'll go through this stuff pretty fast. We've been looking into the reductions in physical demands and whether performance has been affected. But at the same time, we have looked into load transfer risks, and I've said safety in general in the risks category here. Specifically, we've been looking at whether back support exoskeletons, the devices that generate talks about your hip, they pose any fall-related risks, balance, postural stability risks to the user. So we've been doing quite some work on, static balance, walking balance, stair, ascent, descent, and also looking into reactive balance. So we've been releasing people from tethers, we've been putting them on slip trip sorts of equipment and understanding whether the additional hip extension torque about their back is going to impose any sort of delay in how they react to a loss of balance. So that's what I mean by the general term safety in the risks category here. There are other aspects to safety, but this is not even the main point of my talk. So I'm going to try to keep this part fast. We have been severely challenged by the lack of any practical guidelines in this field, as I'm sure everybody in this room has been. And I brought up a few of those in the panel discussion. It is that if we go out into the field and try to do a trial, if it's one kind of assembly task in a controlled manufacturing setting, it's great, right? I mean, if people are always working with their arms above their shoulders, then there's no issue. We have a passive exoskeleton, we put it on and we do all kinds of things. More so as we have started looking into how could exos be implemented in construction and what it would mean to the workers there. That's where we're facing questions of how often do they wear them? How much do they wear them? Is it PPE? Is it a tool? Is it intended to augment performance and whatnot, as I'm sure everybody is aware of. So that's just some background to the kinds of things we've been doing. I wanted to take a number of studies and sort of collapse what sorts of outcome measures we have been looking into in this field. So when the passive exoskeletons are involved, we started with very big picture, task performance kinds of outcomes. And then we moved on to, okay, it's not just about time and errors. Let's look at whether people can still maintain a steady force. Can they still maintain precision? Can their movement still be as smooth and so on? We try to be as broad as possible. So on the subjective end of this, we looked at RPEs. We also looked at how uncomfortable does the exo make you because of how it sits on your body, right? I mean, the effectiveness of the device is closely tied to how well it fits you. And the more it fits you, the more contact pressure and discomfort there can be. So we've looked into perceived discomfort quite a bit, especially with different genders in arm and back support devices. We've looked into various dimensions of usability. And then as we transition to the more objective measures in the lab, like everybody else in the field, we've been looking into kinematics, into muscle activity, a little bit into metabolic energy expenditure as well. And finally, we said, okay, if all this looks okay, I mean, this was the early years of your research, our research, and now we're looking more into what happens with long-term use of the device. Is it going to affect your muscle synergies and your, the coordination mechanisms you have developed over the years in some significant way? Does it affect your spinal stability and so on? So this is really a broad picture of where we come from and what sorts of outcomes we deploy in the lab specifically to look at these devices. This is an example study. People are moving these floorboards from different postures at a certain fixed cycle. They're wearing the Cosmed K5, I think, the device to get at metabolic energy expenditure as well. We're looking at EMGs and asking them a number of subjective questions. And the way we designed this study was to understand whether, first of all, we compared two different passive back support exoskeletons, the BackX from Sutex and the Levo, and we had people perform these tasks at different postures. So what's happening here is that this line here is basically somebody's sagittal plane, and they are performing these lifts at different heights and also at different distances from their body. And we looked at what happens as they twist their trunk through 45 and 90 degrees. I am just giving you a broad brush of the kinds of things we do. So the slide isn't like it should be, but the idea was, depending on working posture, there is quite a bit of difference about whether the exo supports you in the first place. The greener it is, the better it is. As you can see, the bar here shows you how much of a reduction in muscle activity you have about your erector spinae compared to your control, no exoskeleton condition. So the greener, the better. And the red boxes are actually conditions in which the exo makes it worse for you or harder for you to move. So with the passives, we transitioned from the lab, and we are now more at a point where we are looking into applications in the field, what sorts of tasks would benefit from these exos, and what kinds of deployment guidelines can we come up with, and so on. But the main point of my talk today is about our work with active exoskeletons. So what you're seeing here is a powered exoskeleton, a whole body powered exoskeleton. It was, the hardware is made by Sarcos Robotics, and we have worked with them for the last three and a half years on evaluating the device at key milestones along its development, coming up with big picture ideas on what sort of industry would care about a device like this, what sorts of task use cases are ideal, and at the same time asking very detailed questions on what does a human experience physically, psychologically, cognitively while they're in the exo. And we also have a controls team on our end working closely with the company on adding an adaptive high-level controller to the low-level controllers that exist on the part of Sarcos for now. So this is the basic version of the device that we started working with. It weighs quite a bit. It has, today it has 19 active degrees of freedom, but it had 16 at the time we ran some of the tests I'm going to present today. Basically, the device works on what is called a get out of the way control scheme. So there are torque sensors at the major body joints, but there's also load cells at the two hands, at the 2 feet, and about the pelvis. And the exo senses the interaction between the human and the exo at these major places, and then generates a torque to sort of drive that interaction torque to zero. That's essentially the very, very big picture of how this works. No EMGs, no complicated censoring the human other than this. This is the baseline censoring of the system. And I've shown you here about how the system comes together around the human too. So some of the fundamental issues we started with in this case are that the system can give you a lift capacity. I mean, we personally have performed experiments with lift capacities of up to 150 pounds. So you can tune the gains on the controllers to give you more torque output. And of course, as you might expect, we see a trade-off. The more gain you put on the system, the more unstable the system becomes and the worse the user experience becomes. So you can lift 150 pounds, but then you can't really walk being very stable. So it's been a journey of how do we understand how much to get out of the system and at the same time balance a user's sense of control when they're inside the system. You don't want somebody to be strapped into a system and feeling weightless, right? So that's been a big issue that we have dealt with. So this is a rough breakdown of the kinds of things we've been doing. So when we started in 2018, we were more asking what sorts of tasks should we apply this exoskeleton to in the first place to understand how we go about evaluating it and what would our objective be, what would our basic evaluation measures be. Over the course of time, we have looked into questions like how learnable is the exo? How long does it take for a human to go through, get into the exo and feel confident about using it? And I mean, the point was to develop some sort of a training protocol, but then the question also is more philosophical, right? I mean, can you expect to get into an exoskeleton as complicated as this and just it works like you drive a car? Or is it okay for a user to experience 8-10 hours of training time to just get up to speed with the exo? And yeah, we've been going down that direction. And the outcome measures we have typically used include EMGs and IMU sensors to look into kinematics and physical demands. We have been interested in how synchronized the human and the robot's kinematics are. We have the sensors from the robot, and we've been using IMUs on the human to get at this problem. We realized early on that there is a significant cognitive demand on the user to control an exoskeleton as big and complex as this. So we started by looking into people's gaze eye tracking measures to see if we could get at cognitive load. We've also used some subjective responses to get at the same. So this is an example experimental protocol where we had a healthy sample of about 15 individuals. This has happened at various periods of time. We trained them to operate the exo over at least 5 sessions, lasting a total of over 10 hours. And I'd like to show you some results of both what happened during the training and what happened after the training. And these are some typical examples of tasks they were doing. So here the person is lifting and manipulating a load of around 110 pounds, I think, but we varied the load across a range. So this is just a person standing stationary, but we are trying to make them go through a range of postures just to sort of see whether the exo is limiting your range of motion in any way, but also measuring what I've been talking about. This is another task where somebody is carrying a suitcase. They're carrying actually a bag between their arms, and they're doing classical load carriage. They're walking back and forth on a track, and you see the human and the exo from our kinematics. And there was supposed to be a third picture here. Yeah, this is just a classical fits task kind of paradigm where they're wearing the exo and they are going back and forth between targets. This was one of the few protocols where we had a chance to also manipulate target precision and how people dealt with precision demands when they were in a sort of intense and heavy device like this. So moving on to some results, these were quotes from our interviews with the people that were getting trained to use the device. So when they started out for the first 4 or 5 sessions, we asked them right after each session, what do you think? And these are the quotes that popped out for us, which told us that we were not wrong in thinking we needed to track cognitive load as well, in addition to physical load. And from the load carriage task, these are some results of the EMGs. So we're not, just to clarify, we're not using EMGs here for control. We used EMGs just to assess a person's experience in the exoskeleton. And what you see here is that people were doing load carriage across a range of loads, going all the way from 10 pounds to 60 pounds. We stopped at 60 because we were also having them do no exoskeleton trials. We didn't want to go over 60. So the red lines are showing you the average muscle activity in the left and right thoracic erector spinae and the lumbar on the bottom panel. So the red lines are the baseline or the no exoskeleton condition. And the blue lines you're seeing here are the average across the individuals of what their muscle activity levels were at when they were using the exoskeleton. Each person had the exo tuned personally to them because they had so many hours with the exoskeleton. We could tune the exo and fit it according to their own user preferences. And that process took us quite some time. So, but for what it is worth, you can see here that I don't even show the inter-individual variance in the no exoskeleton condition because these EMGs are normalized to people's MVCs. And the variance band in the no exo basically filled up the whole chart. But the key findings when we had the exo on were two. One was that the exo seemed to actually have some sort of baseline load level in the muscles that did not go away. So you began to see benefits of using the exoskeleton only when you crossed a certain load. So if you think about a very low load, less than 20, 25 pounds, maybe the exo is not as useful. And why would you wear a device like this to lift less than 20 pounds? But if you went over, then you began to see quite significant benefits of using the exoskeleton in some cases. And the other finding was that the inter-individual variance across individuals actually dramatically decreased when the exoskeleton was deployed. And we are still trying to understand whether that's because people started behaving the same way when they used an exoskeleton. I mean, maybe they ran out of strategies, and so we lost some healthy variability there, or whether it is because the exo's contribution to the task so far outweighed what the user was putting out that the variance across users came down. This is something we're looking into. We also have similar results from the leg muscles. We looked at the quads and the hamstrings, as well as some the tibialis anterior and the calf muscle, and we had some issues with the ankle joint of the exoskeleton at the time we ran these tests. So the tibialis anterior, if you see, was quite significantly loaded, close to around 40% maximum throughout the trial that we ran. So I mean, these are not like the final results of the exo. The exo still continues to get improved upon, and it is evolving in design, both in hardware and software, but it is just a snapshot of how the EXO was in 2020. And I'm using this as just to explain what kinds of things we're doing with an exoskeleton, what kinds of considerations might be needed. I told you that we were also looking at cognitive demands. Megan, how am I doing on time? How much more time do you think I should? I'm okay? Okay.
Yeah, take what you need, yeah.
All right, thank you. This is people's mental demands on the NASA TLX as they were using the exos over the 5 sessions. I told you we had 5 training sessions. This is how they rated their no exoskeleton mental demands as they were performing a task. I think this is actually from the FITS task that I showed you. And in session 1, even to do something like just tap between targets, people were experiencing quite high mental demand that went down over sessions. Like in session 5, it was better than session 1, but it wasn't ever as low as what it was without an exo. I mean, and I'm making this point because maybe in session 6, it would have looked like the exo, but 10 hours of training is pretty significant. And at 10 hours, people still weren't as comfortable using the device to do even something basic, like just, point their hand between targets. So that's one thing. We also looked at how it looks like when somebody uses the exo to do the FITS task in terms of their gaze transitions. So what you're seeing here, there were 2 targets like these under these. This is a heat map from somebody's eye tracking data. And it shows you essentially that once people became super comfortable with the exoskeleton, and this is not a person from our study, this is a person who was involved in the design of the exoskeleton. So they'd used this exo from the day it existed for years. And this is how their eye tracking data looks like in terms of where they're looking at when they're doing the FITS task. Essentially, for a normal human, if you're going to point between targets, you just need to look at the targets, right? You don't need to look at anything else. And this is our eye tracking data from a participant in our experiment while they were, in a classical session 2 or session 3. And what you're seeing here is that in addition to looking at the targets for most of the time, the user of the exoskeleton is not able, I mean, this is our hypothesis, they are not able to develop a good enough mental model of where the exoskeleton's end effector is. And so in addition to looking at targets, they are actually looking at where their end effector is or where their hand is in the classical sense. And this has been shown by several motor control studies that until you develop, a good enough mental model, you're either breaking down a complex movement into multiple sequential steps and you're performing them in steps, or in this case, if you cannot track the end effector well enough with your brain, then you're still tracking the end effector with your hands, with your eyes, and that's how you're performing the motion. So this is something that told us that our expectation that people were having a hard time understanding where or what the exoskeleton was doing is true, even for as simple a task as pointing between targets. And these are results from pupil diameter. So we used the eye tracking data for two reasons. One was we wanted to see what sort of strategies were people using as they were using the exo to perform movements. And the second was, could we estimate some sort of mental workload from the eye tracking data? And pupil diameter has been shown to be something that could be useful for estimating how hard somebody is working or how stressed they are when they're doing what they're doing. And you see here that the pupil diameter does sort of go down over the sessions, but just like the NASA TLX showed, it doesn't quite reach the level of the no exoskeleton condition even after all these hours. We also have some data from basic tasks, like can you match the force if you had one arm in the exo and one arm without, can you actually match what your non-exo arm is doing with your exo arm? That is something we have looked into. Can you perceive how much your own spatial envelope is? So if you're wearing the device and you're asked to clear a doorway, we construct like cardboard stands and ask a person to first estimate whether they think they can clear it. And then they actually do the task and either knock over the cardboard or they're able to do it successfully. So we've looked into, can people estimate how much their spatial envelope is when they are in the device? Can they perceive time? So if you have objects moving on a trolley, or if it's just a conveyor belt, can you get out there and pick up something with a correct estimation of how long it's going to take for you to generate and perform the movement? I was looking for a word that started with an E, but I didn't find it this morning. And finally, we are looking at dual tasking too, for obvious reasons, that when you are so focused on controlling this device and trying to understand how it's going to behave, it's very likely that your situational awareness of what is going on around you has greatly decreased. So as people are engaging in low carriage or even in just walking down a ramp, we're looking at whether they can still perceive a light going off or a sound going off that they would have normally been aware of. So these are more, I wouldn't say these are basic assessments of somebody's cognition. I would say these are more driven by our understanding of how is safety going to be impacted. If this exoskeleton were going to be used in an industrial setting tomorrow, like what are the things we need to be aware of where people's perceptions are compromised, so that if we were to give them some sort of a task, what would we need to be aware of that they might lose or miss out on? So this is my last slide. I will stop here. Essentially, the challenges we are facing are that the EXO is continuing to evolve and improve, and we ourselves have participated in several iterations of the design and development cycle. So now we are at a point where we are asking, we have created a model of the device, and we are trying to run some simulations on anybody. So the question is, when do we stop with the simulation? When do we go and do human testing? And how often can we do it, right? So there is a practical challenge here in how much human testing is needed, but also when it is needed to move the design forward in a good way. We are still stuck at a point where the way the EXO needs to be tuned for each user is a process that takes a few hours. I mean, there's so many things going on across all the joints, across how a person likes the device to sit on their bodies, across what they need for balance versus what they would like for handling an object. So those are some issues we are trying to work out, like how do we even begin to optimize this process. And the final is, there is a clear difference between how users sort of evolve with the device. So there's some people who get into it and within 2 hours they feel like they're getting somewhere, and there are others who even after 10 hours, they sweat even when we tell them they have to get into the device. I mean, they don't have to, but would you like to get into the device? And they begin to sweat because there are issues. There is a sort of a tangible delay between what you're doing and what the EXO is doing that can really sort of put you off. The other issue we have is also that the EXO is not self-balancing. So the EXO takes away the load of, I mean, you don't feel 200 pounds on your body, but you feel it's inertia. So you are responsible for balancing yourself and the exoskeleton, which is so non-trivial that it just works for some people and it never does for some others. And those are issues we're still trying to figure out. So I'll stop here. Thank you for listening to me, and I'm happy to have some discussions around these things.
Excellent. Thank you so much, Divya. So yeah, we'll open it up to questions, both for Divya as well as for Patricia and for Sasha. And maybe as we wait for some questions to come in, I have a question that was spurred by Sasha and Patricia's talk. And then I think this point you kind of brought up, your last point at the end, Divya, I think is very applicable too. Before today, I hadn't really thought about when we give humans this additional capability, what the expectations are going to be and how they might change for the worker. And then especially like, right, so if you have a robot next to you or a robot assisting you, are you expected to do more? But then you also have this other issue of, but what if you are not as successful as learning how to use the robot or not? And how does that play, how does it affect you as an employee? So I don't know if you have any comments on that, but again, it was something that kind of struck me. I never thought about that before.
Yes. Thank you for bringing that up, Megan. I think one of the fears that I have is that from a designer's perspective, it seems like it's obvious, right? So the first thing they say is the EXO is designed so that you just put it on and you're good to go. Like that's how it's going to be designed. I know that's never happens, and it's definitely not the case for devices like these. But then the issue is the onus on the human to somehow learn to, operate this device, or is it actually on the designer to make sure the device is learnable in a decent amount of time? And we're still struggling with that. How much of it is on the human? I mean, suddenly is it going to be like, if you can't, get into this device without getting scared, you won't have a job? Like that's so nightmarish, such a scenario, that I think this is going to come up more and more as power exos become more of the norm. With passives, it's probably less of a problem, but with power devices, if you can't balance in an exo, I mean, you might be really good at the job you're doing, but what is going to happen if this becomes the norm?
Yeah.
Yeah, I think this is, it's a very good point. And I think we heard this this morning from Jose. I think he named very well to manage the expectations, because I think this really goes in different directions. So on the one hand, you expect from exoskeletons, robotic systems, you probably have this like Hollywood shaped stereotype in your head, where you think these systems are capable of doing anything. You might be capable of doing anything then, but then on the other hand, especially in the work situation, you have a very specific situation, because it's also about, is it your performance? Is it the system's performance? Do you get judged? As I said, this topic of surveillance, because as systems get adaptive, they know something about you, and what's happening with this data, what's happening with this knowledge. These are questions which have to be dealt with, and people ask themselves. So especially in the work situation, I think it's always a double-edged sword, because if it's more in the private area, then of course we might be willing to hand in more data. We're not so concerned. But within the work situation, of course, we might be more concerned. And I think we always have to have in mind, are we facing systems which are more for the private use or for the occupational use? It's something completely different from my perspective.
Excellent. So I have you or Michael have to battle it out. Who's you can go, Serena.
I raised the hand first. No, sorry.
Okay, yeah.
So I have a question. So actually 2 questions for Divya. So first, great talk. I'm super excited now. I want to have a powered exoskeleton. Actually, I tried one. So my questions are also biased by my experience with the power exoskeleton that I tried in Japan, that allowed me to lift 60 kilos without feeling anything. So the first question is, it was pneumatic. So at some point you said, I noted, the more payload you have, the less usable and more unstable is the system. So the question for me is it because when you move, for example, carrying a payload, you don't know anymore how to move in a proper way? And so at the end you're unstable. Like, for example, if you know that you're lifting 20 kilos, so your body knows about this information, so plans a movement that matches this payload. But at the end, if you're using an exoskeleton, you know that you're lifting 20 kilos, but you feel only 1 kilo, for example. And so at the end, there is a mismatch. And so this mismatch, at least in my experience, was causing a sort of cognitive problem, like motor problem. Like I was carrying this 60-kilo box like everywhere. And they were like, no, don't move like that. And I didn't realize I was moving in a bad way. So I don't know if this question of instability is due to that, plus, of course, to the fact that you said that the exoskeleton is not self-balancing.
That's a great question, Serena. And obviously, it's a question from somebody who's been in a device like this before. I think a bit of both is happening. Of course, if you don't understand what load you're lifting, the load is still carrying its inertia, but you mentally are unaware of it. It's possible that you're moving in a non-good way, right? Because you don't exactly estimate how much you're carrying. So one of the questions we asked is, if we just inform somebody of the actual load they're carrying, not what they feel they're carrying, will that help in any way? But then the second problem is also that if you ramp up the gain on the actuators to, bring down your loading when you're carrying that load, then the actuators are also amplifying every little noise in the system, right? So the system becomes so unrealistically sensitive to what you're doing that even if you're just stationary and you do something with the load, it seems okay. But when you start walking, it's walking that gives us the trouble. And that's intricately tied to how sensitive the exo is and how well you're able to balance yourself. So
and so this is because you increase the gains of the PID, but like the stiffness or like the gains in the intercontrol, but you don't have a system like with damping.
Yeah, so I think the problem is also that now we are trying to independently have the exo sense what the load the human is operating at, rather than only sense the interaction torque. So then if the exo knows that it's a 60-pound or 60-kilo object, then we can sort of tune down the controllers in a way that makes sense for the motion. So because we had both the human and the robot kinematics, we could start distinguishing how much of this is because the human's moving differently versus how much of it is being caused by the exo. But it's like a chicken and egg problem, right? You don't know if the human is inputting the wrong sorts of things, so the exo is amplifying them in the wrong way. But yeah, both are issues.
Okay, and the second question, and then I leave to others because I have many, but because at some point in the gaze tracking task, so you were looking at the heat maps, and so you said that they look at the target, but they are also looking at their ends. And so this reminded me of what Ganesh was saying. So if they still look at the end, it means, and this is a question, like, does it mean that they still think that there is no symbiosis? So it's not embodied. They haven't reached the level at which they know where the hand will be.
I think that is what it is. I mean, they are holding on to the exoskeleton, and if the normal way you execute a motion is that if you are starting, there is something in your motor system that sort of predicts what the trajectory is about to be and how your hand is moving, right? So you know how your hand is going to follow and you directly look at where you need to go. But if because of the exo doing its own thing in addition to your motion, you can't predict where your hand is going to be forward in time, then I feel like you're coming back and checking where your hand is at a few instants in time just to get to your target. So that's how
even after 10 hours of training, they don't develop this.
This was more at like hour 4, hour 5. It wasn't at the end of 10 hours. We are plowing through the data to see, is there a point in the training at which this goes away? We haven't found one for every person. That's the problem also that we're having, that for some people at 5 hours of training, this kind of a thing goes away and they have managed, and then you see their heat map begins to look like the experts. And for others, it is, at 10 hours, it still looks like what I showed you. So that's why I said there are such different trajectories on how fast people learn with the system, that now we're asking, what is it? Like, why are people showing so much difference in how comfortable they become with the system?
Wow, thanks. There was the other question by Michael.
Hi everyone. I certainly feel a little bit out of place as a mere PhD student, but I want to thank you all for having me just over all the wonderful talks today. So I had one question that actually is brought up by one of your early slides, Divya, but it certainly relates to your work as well, Sasha and Patricia. So in thinking, throughout this whole workshop, I think we've seen a lot of different metrics for evaluation. We've seen cognitive metrics, EMG, muscle exertion, surveys, pupillography. So it seems to really comprise of quite a broad set of experimentation that's being used to evaluate these wearable devices. So I was just wondering, I was curious to hear your thoughts on, when thinking about what sort of metrics we want to show to kind of promote adoption of these devices. Do you think that, that set exists within the current batch of methods that we've talked about today? Is it a subset, or do you think there are areas of evaluation that currently aren't being captured that you think need to be evaluated to really encourage adoption of these devices in industry?
Oh, that's a tough one. That's a tough one. I just try with a start of an answer. Well, I think if we go to the subjective questionnaires, I think we have plenty of questionnaires out there on trust in automation, on usability, on dialogue principles, on all these issues. And I think they work pretty well. So I would say in that field, also what we just saw, the NASA TLX. Also all these different kind of measurements. So I would say we have a broad knowledge of tools out there, technology acceptance model questionnaires there. So I think these subjective measures are always very valuable, also for this part of worker participation. Because of course, what we saw today, also collecting physical measurements, heart rate, or any kind of EMG, anything. I mean, if you get connected to these kind of systems, and well, these kind of signals get collected easily, so that you don't basically feel it, then it's good to collect these data and to use it. But the moment, well, you need to measure it, and it's very complex. You have to attach other things to the human body. It is very difficult, I would say, and then you have to look very carefully if you really measure the proper thing, because most of very often people want to measure the cognitive workload, and measuring cognitive workload with psychophysics is really very difficult if we are moving to the field. So that's why we work a lot with subjective questionnaires and surveys if we move to the field, because yeah, everything that is psychophysics is really difficult from our experience.
Just something that I would like to add to that, Michael, is also that we are also exploring to see how much of this can be done without censoring the human, right? There's always the question of, can we censor the heck out of the robot and just have the robot track whatever it is that needs to be tracked? But obviously that is hard because we don't know, we are not even at a point where we know whether it's the physical load or the cognitive load that's going to pose a safety risk on a human. And of course that changes from human to human. So it's like, I don't know how many more years of research, but many of us in this room are still young. So hopefully we keep plowing that away.
Any other questions? I do have one, it's kind of specific, but to piggyback off of what Serena had asked. So in the gaze tracking, and you mentioned that you have these possible, that's due to like these potentially like sub movements, right? Have you looked at the velocity patterns and how that correlates with the actual positions of these eye movements?
That's a great question, Megan. That is, yeah, that would have been on another slide. I tried to compress many talks in one talk because I wanted to get the broadest picture here. So yes, the velocity profile of the movement conveys the same story, that there are like the whole task is being planned in sub-movements. So the hand kinematics actually nicely shows you not one bell shape, but multiple smaller bell shapes that show you that the movement is being somewhat sequentially planned rather than being like, one smooth movement from the target to another. So yeah, the hand kinematics is what helped us sort of confirm that that story is true.
That's awesome, because I know, well, anyway, it's great to know, because I know people who are working on sub-movement decomposition, that can be really challenging, and so fitting these sub movements, but hadn't thought about, can you also use gaze as another indicator to help with fitting that? So awesome, thank you. Any other final questions? No? Awesome.
I think you might as well wrap it up.
Yeah, tired.
Yes.